Hi, in this video we are going to derive the expression of the inverse Fourier transform. That means, suppose that we have a Fourier transform expression x of omega. How can we obtain x of t from x of omega? The integral expression will be named as the inverse Fourier transform. Okay, so we start the derivation by noting a parallelism between the Fourier series and the Fourier transform. Okay, the analysis will be as follows. Now let us start with an x of t, a signal x of t with a finite duration. So let x of t be a finite duration signal. Which is completely arbitrary other than this restriction given as, okay, we don't need to specify it analytically, just graphically it is an arbitrary, completely arbitrary signal, but with a certain finite duration. So we have such a signal. Okay. Now we can obtain a periodic signal by means of the periodic extension of x of t as follows. So let x p of t be the periodic extension of x of t defined as follows, defined as xp of t is equal to m from minus infinity to plus infinity, x of t minus m t0. So we have the periodic extension of x of t with a fundamental period equal to capital T0. So graphically we have the following graphical representation. So this is t, this is xp of t. So it will be this signal repeated periodically with a period, a fundamental period, capital T0. So we have the periodic repetitions of x of t with fundamental period T0. Okay, so xp of t is defined in this way. Now xp of t has the Fourier series representation. So let omega z0 be 2 pi over t0, and we will have the Fourier series representation of xp of t as follows: k from minus infinity to plus infinity, ak e to j k omega 0 t. Okay, the coefficients ak can be obtained from xp of t, remember we integrate over a period from minus t0 over 2 to t0 over 2, xp of t e to minus jk omega 0 t integrated with respect to t. Okay. Now, xp of t just look at the integration interval. It is from minus t0 over 2 to t0 over 2. So we can plot those 2 points on the graph. So we have minus t0 over 2 to t0 over 2. Over that interval, x p of t is equal to x of t. So xp of t is equal to x of t for t in the interval from minus t0 over 2 to t0 over 2. Okay? So ak can be replaced as 1 over t0 from minus t0 over 2 to t0 over 2, x of t e to minus jk omega 0 t integrated with respect to t. However, we know that x of t is 0 outside this interval if we look at the graph of x of t. So, equivalently, ak can be written as 1 over t0 from, instead of minus t0 over 2 to t0 over 2, we have the integral from minus infinity to plus infinity, x of t e to minus jk omega 0 t integrated with respect to t. But we recognize this expression here as the Fourier transform of x of t evaluated at k omega 0. So this expression is simply capital X of k omega 0, Fourier transform of x of t evaluated at k omega 0. Therefore, ak is equal to 1 over t0, capital X of k omega 0. So this establishes a nice relationship between the Fourier transform of a finite duration signal and the Fourier coefficients of its periodic extension. Okay. Now we can substitute this ak in the Fourier series, and then the next step will be to look at this expression when t0 gets larger values. So when t0 tends to infinity, we will see that the series will tend to an integral which will be named as the inverse Fourier transform. So now let us look at the details of this part of our derivation. Okay, so ak is 1 over t0, capital X evaluated at k omega 0. Now we can substitute this in the Fourier series of xp of t. xp of t is equal to k from minus infinity to plus infinity, 1 over t0, capital X of k omega 0, e to j k omega 0 t. Now, T0 is equal to, remember, 2 pi over omega 0. So instead of 1 over T0, we can write omega 0 divided by 2 pi. Now at the same time, we know that omega 0 is equal to k plus 1 omega 0 minus k omega 0. In other words, it is the increment between the frequencies k plus 1 times omega 0 and k omega 0. So we can call this expression as the frequency increment delta omega. But before doing that, okay, let us write down the expression once more. Xp of t is equal to k from minus infinity to plus infinity. Maybe we can just take 1 over 2 pi outside this expression. And then we have k from minus infinity to plus infinity. We have capital X of k omega 0 e to j k omega 0 t. And then we have the expression k plus 1 omega 0 minus k omega 0. Now, we know that when T0 tends to infinity, xp of t will tend to x of t. Remember, xp of t is the periodic extension with period T0. So when we increase the period and in the limit as the period tends to infinity, xp of t will tend to x of t, and if we look at the term omega 0, omega 0 will tend to a very small value when T0 gets larger in value, and in the limit as T0 tends to infinity, omega 0 will tend to 0. So this is here, this can be written as omega 0 as well, but it is in fact nothing but the frequency increment. The frequency increment delta omega will tend to the differential element d omega. Okay, so k omega 0 can be replaced by the variable omega, which is the continuous variable now, because the frequency points k omega 0 will tend to each other. K omega 0 will be very close to k plus 1 omega 0. And in the limit, the discrete frequencies will tend to a continuum. And k plus 1 omega 0 minus k omega 0, which is in fact the frequency increment, we can show it by delta of omega, will tend to d omega. Okay? and eventually the series will tend to the integral xp of t will tend to x of t equal to 1 over 2 pi the integral from minus infinity to plus infinity x of omega e to j omega t integrated with respect to omega. Now this expression is called the inverse Fourier transform expression or inverse Fourier transform integral, which is called the inverse Fourier transform expression. Okay, so this means that whenever x of omega is given, we can calculate x of t from x of omega by means of this integral, which is called the inverse Fourier transform. Okay, now next we are going to introduce some notation for the Fourier transform and the inverse Fourier transform, and see an example, an important example related to the usage of inverse Fourier transform. So now let us continue with these details. Okay, so now we have the Fourier transform expression and the inverse Fourier transform expression. So these are two integral transforms expressed in terms of the following pair. So we have x of omega equal to from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t, and x of t is equal to 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t integrated with respect to omega. Now, so the first expression is the Fourier transform expression. The second one is the inverse Fourier transform expression. Now, intuitively, it is very important to observe the following. Now, we have interpreted the Fourier transform as a measure of how much e to j omega t is contained in x of t. So when you evaluate the Fourier transform, you calculate this quantity. Then, in the inverse Fourier transform, if you look at the expression carefully, this is an integral, but it can be interpreted as a generalized superposition of the terms capital X of omega multiplied by e to j omega t. Now remember that x of omega is a measure of how much e to j omega t is contained in x of t. So e to j omega t multiplied by this quantity is just that part of the signal. Now we superpose all of these terms by means of the inverse Fourier transform integral and synthesize x of t. Okay? So capital X of omega is called the Fourier transform of x of t, and it is also interpreted as the analysis equation. We analyze the signal by calculating how much e to j omega t is contained in x of t. Then we have x of t. This is the inverse Fourier transform of x of omega, and it can be interpreted as synthesizing the signal x of t by means of the frequency components. Because x of omega is a measure of how much e to j omega t is contained in x of t. So we superpose all these components to obtain x of t back from the frequency components. Now also we have the following notations found in several books in the literature. I'm going to write rather notations because there are different notations. One notation is to use the this arrow with the double arrow to just express the Fourier transform pair x of t and x of omega. Remember, we did this we used this notation in the Fourier series as the relationship between x of t and the Fourier series coefficients. Another notation is x of omega is the Fourier transform of x of t. So this script f denotes the Fourier transform operation, or x of t equal to the inverse Fourier transform, script f to minus 1 of x of omega. So these are all some notations used in the literature. So instead of script f in certain books or articles in the literature, x of omega is shown as ft of x of t. So ft denotes the Fourier transform, and x of t is ft minus 1 x of omega. So these are typical notations used in the literature. Now let us see an example, which is an important example. Now we have seen that the Fourier transform of the impulse is equal to 1. That means in the impulse we have all frequency components for omega from minus infinity to plus infinity represented with the same weight. Now, we ask the following question. Let x of omega be given as delta of omega. Find x of t. In other words, find the signal whose Fourier transform is delta of omega. Delta of omega means what? It is 0 everywhere for all frequencies except omega equal to 0, where it is infinite. So x of t can be evaluated by means of the inverse Fourier transform. 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t integrated with respect to t. So this is equal to delta of omega. Sorry, not t. The integral is with respect to omega, of course, in the inverse Fourier transform. Okay, so x of t is equal to 1 over 2 pi. So it is a constant signal for all values of t extending from minus infinity to plus infinity. X of t is equal to 1 over 2 pi. Now, if you do not like this 2 pi expression here, originally we could have started the example as follows. Let x of omega be equal to 2 pi delta of omega. So the impulse has weight equal to 2 pi. And we will end up with 1 in that case. So by using our notation, Fourier transform of 1 over 2 pi is delta of omega. But if you do not like this 2 pi over there, we can write this equivalently in the following form. Fourier transform of 1, the constant function, which is x of t equal to 1 for all t, is equal to 2 pi delta of omega. Now we clearly see the interpretation of the Fourier transform in this example. Now 1 is, the constant signal is a DC signal. It is not changing with respect to time. It is equal to 1 for all t from minus infinity to plus infinity. Therefore, remember, the frequency components are denoting the weight of e to j omega t within this signal. Now, for all omega different from 0, e to j omega t will correspond to, remember, the real part is the cosine signal, the imaginary part is the sine signal, so we have sinusoidal oscillations. But here we have a constant signal. Therefore, the constant signal, the only non-zero component is at omega equal to 0, which is the zero frequency, and there the weight is infinite. Okay? Now here, in a way, we are starting to see a certain relationship between the so-called time domain and frequency domain expressions. That means the signal and its Fourier transform. The Fourier transform of the impulse delta of t is equal to 1. Now also we have to compare this with that as well. Remember that Fourier transform of the impulse is equal to 1. Now remember, in time domain, an impulse means it is a zero duration signal which is infinite at t equal to 0, and then everywhere it is equal to 0. So its Fourier transform is equal to 1. So all frequency components are present in that case to establish the singular behavior of the signal, being 0 for negative values, and suddenly it jumps to infinity and drops back instantaneously to 0. So these fluctuations and the singular behavior is established by means of the contributions of all frequency components for frequencies extending from minus infinity to plus infinity. All of them are present in the signal with equal weight. But on the other extreme, the Fourier transform of the constant one is an impulse in the frequency domain. So in that case, we have only the zero frequency component, but with infinite weight. Okay, so this relationship between time and frequency domains will be much more apparent in our future videos, studies. Okay, thanks for watching.